So we have this question. It says that number of cyclic groups of the quaternion group Q8 is. So we have to find out cyclic subgroups of Q8. So if I'll see Q8, what will be Q8 here? Q8 will be plus minus 1, plus minus j, and plus minus I, and plus minus k. This is my Q8, right? And I know that Q is not abelian. I, because if I'll do I into j, I'll get k, and if I'll do j into I, I'll get minus k, right? So that means they are not commutative. So Q8 is not abelian. That means Q8 is not cyclic, and I can find out all the subgroups. So let's first find out all the subgroups, and then I'll see that they are cyclic or not. So if I'll see subgroups of Q8 will be plus minus 1 will be a subgroup, 1 will be a subgroup identity, and then we have a plus minus 1 and plus minus I. It will be a subgroup, and we have another subgroup which is plus minus 1 and plus minus j, and this will be plus minus 1 and plus minus k, and then later on we have Q8. So these are all the subgroups of Q8. So if I'll see this, it is generated by minus 1. This is an identity, so it is generated by an identity. And if you will see this subgroup plus minus 1 and plus minus I, it is generated by I. Similarly, this subgroup is generated by J, and this subgroup is generated by K. I can check that because order of J, K, I is 4, and this subgroup has 4 elements, right? So all the subgroups, all the proper subgroups are cyclics. So if I'll leave Q8, I'll get all the subgroups cyclic. So if there is all subgroups cyclic, so how many subgroups? 1, 2, 3, 4, and 5. I have 5 subgroups of Q8 which are cyclic. So here 5 is my correct answer. We have this question. It says that number of elements of order 3 in the symmetric group S6 is. So we have to find out how many elements are there of order 3 in S6. So I know that if I have to find out number of elements in any permutation Sn, number of elements of, let's say, particular order K, number of elements of order K in Sn, that would be n factorial 1 to the power alpha 1, 2 to the power alpha 2, and ongoing in this way, and alpha 1 factorial and alpha 2 factorial, right? So this is a formula where alpha I is equals to, number of cycles of length I, number of cycles of length I. So you will ask that, okay, so we have this formula. If we have this formula, there is no particularly order k, and how we will get this number of cycles of length I. So first of all, I can found a partition of 6. I can found a partition of 6 here. So what will be the partition? I have to find out partition of 6 such that I'll get this order 3. So I'll get LCM 3. So if I'll take the partition of 6, so if I'll take 3 plus 3, I'll get LCM 6, LCM 3, right? I'll get LCM 3 comma 3 is 3, right? So uh, I have here cycles of or elements of order 3 here, right? And alpha I is equals to here 1, 3 square, that means 2. Okay, so next we have is another partition we have is 1 plus 1 plus 1 plus 3. This is again, if I'll take LCM of 1 comma 1 comma 1 comma 3, I'll get 3. So I'll get here elements of order 3. So these two only partition exist which will give me of order 3, right? Elements of order 3. Now I have to find out elements of order 3. So how would I do that? Using this formula, right? Let's see. 6 factorial 1 to the power alpha 1, 2 to the power alpha 2, where alpha is equals to number of cycles of length I. So if I'll see here, I have 2 cycles of length 3. So that means 3 square, and into L5 factorial, that means 2 factorial, right? And in corresponding to this, we have 6 factorial. We have 1 cycle of length 3. We have three cycles of one length, right? So that means one cube and three, we have one cycle of length 3 to the power 1, and then we have 3 factorial into 1 factorial, right? Now I can solve this. Let's solve this. 6 into 5 into 4, and we are left with here 3. Here we'll have 6 into 5 into 4 into 3 into 2, and then we have 9 into 2 here. 3 2 just 6, we'll get 40 here. And if I'll calculate from here, I'll get 2 and 2 get cancelled. 3 3 just 9 and 3 2 just 6. Again from here I'll get 40. So in total we have 40 plus 40 elements. So here I'll write 80 elements. So there exist 80 elements of order 3 in symmetric group S6. Right, so to solve these type of question, we just have to remember this formula to find out number of elements of a particular order. Yeah, so we have this question. It says that F be a field with 4096 elements, and we have to find out number of proper subfields of S. So we have one formula for proper subfield. It says that if, let's suppose, order of F is equals to P to the power n, right? Then number of subfields, then number of subfields of F, number of subfields of F is equals to number of divisors of n, total number of divisors on of n, right? And I can find out this using tau n, right? And what is tau n? Let's suppose if n is equals to p1 to the power e1, that means this is a prime factorization. P2 to the power e2, this is a prime factorization of n. Then I can find out tau n using e1 plus 1, e2 plus 1, and then we have ongoing in this way er plus 1, right? So we have this formula for number of subfields. So let's apply this in our question. So here I'll have order of F is equals to, order of F is equals to 4096. I can write this as 2 to the power 12, right? So if I have to find out number of subfields, that would be number of subfields, that would be tau 12, right? And how would I find tau 12? 12 will be equals to 2 square into 3, right? So that would be tau 12 will be 2 plus 1 and 1 plus 1. So from here I'll get 6. But if you will see here, they ask me to find out number of proper subfields. We know that total number of subfield is 6. And if I have to find out proper subfield, I have to subtract 1. So what would I get from here? To find out proper subfield, proper, right? I'll have to subtract 1. So I'll get the answer as 5. So 5 is my correct answer here.